Replacement of cement with wheat straw ash, WSA, in-house construction process. Studies have been carried out to see whether wheat straw ash, a common agricultural waste, can be used as a sustainable replacement for part of the cement in concrete. Cement production is a major source of global carbon dioxide emissions, so finding ways to reduce its use is crucial for the environment. Wheat straw, left over after harvesting wheat, is often burned in open fields, causing air pollution. Instead of wasting it, this research explores turning this ash into a useful building material. The researchers collected local wheat straw from Pakistan and burned it at 3 different temperatures: 550 degrees Celsius, 650 degrees Celsius, and 750 degrees Celsius. The goal was to find the best temperature that would produce ash rich in silica, which is essential for pozzolanic activity. Pozzolanic materials react with lime, a byproduct of cement hydration, to form strong compounds that improve concrete over time. Analysis showed that ash burned at 550 degrees Celsius had the most desirable structure. It was highly amorphous, glassy, meaning its silica particles were not locked into rigid crystals, making them more reactive. Ash burned at higher temperatures became too crystalline and lost this valuable property. This optimal ash was then ground very fine, similar to the texture of cement powder, to maximize its surface area and reactivity. The finely ground wheat straw ash from 550 degrees Celsius was then mixed into mortar, a mixture of cement, sand, and water, and concrete, mortar plus gravel and sand, at 4 different levels, replacing 15%, 20%, 25%, and 30% of the cement. The performance of these mixtures was compared to standard concrete made with only cement. Up to 20% cement replaced with wheat straw ash matched control strength early, 15% surpassed it at 28 to 91 days as reactive silica densified the paste, while 25 to 30% replacements were consistently weaker. Importantly, even though mortars with 20%, 25%, and 30% WSA were weaker than pure cement, they still met international standards for pozzolanic materials. This means they are chemically active enough to contribute positively to the concrete's long-term properties, even if they don't immediately match the strength of pure cement. In concrete, 15 to 20% wheat straw ash lagged at 7 to 28 day, but 20% overtook control at 91 day. Classic slow pozzolanic gain, 25 to 30% stayed weak. The same mixes matched or bettered control stiffness and toughness, 15% notably boosting 91 day ductility. Paste tests showed 15% ash consumed the most lime, 20% was next, confirming their reactivity. Higher doses were less reactive. The porosity, amount of empty space, of the mortars was also measured. Lower porosity means a denser, stronger, and more durable material. The mortar with 15% wheat straw ash had the lowest porosity at 28 and 91 days, directly explaining its superior strength and durability. Higher WSA percentages led to increased porosity, correlating with their weaker performance. In conclusion, this research demonstrates that locally available wheat straw ash, when properly processed by burning at 550 degrees Celsius and grinding finely, can be a viable and sustainable substitute for cement in normal-strength concrete. Replacing up to 15% of the cement with wheat straw ash improves long-term strength, reduces porosity, and enhances toughness. Even replacing 20% works well, particularly in terms of ultimate strength and durability, meeting industry standards for pozzolanic materials. While higher replacements, 25 to 30%, lead to weaker concrete, the ash itself is still chemically active. Therefore, using wheat straw ash as a partial cement replacement up to 20% is a practical way to turn an environmental waste problem into a resource for greener, more sustainable construction, especially for common buildings where extremely high early strength isn't critical.